Hello everyone, and welcome to another experiment from Saturday morning astrophysics at Purdue. This time around, we're going to take a look at a phenomenon very closely related to astronomy, the Doppler effect. The Doppler effect is a phenomenon of waves, sound waves, light waves, gravitational waves, and is observed when either the source of the wave or the observer is moving relative to the other. Let's use a spring slinky as a model for a wave. We have a source and we have an observer. And as the source gets closer to the observer, you see that the wavelengths get shorter. And as the source moves further away, the wavelengths get longer. So as the source of sound approaches the observer, the waves are squeezed together for a shorter wavelength and a higher frequency. And as the sound source passes by, the waves are more stretched out, which we would hear as a lower frequency and a longer wavelength. Astronomers are more interested in light than in sound. There is no sound in space, but we can explore the phenomenon of the Doppler effect with sound using a free mobile app called Phyphox. In the written handout that accompanies this video, we'll show you where to get Phyphox, how to install it, how to use it, and how to do our simple experiment. All you need to do the experiment is a mobile phone with the Phyphox app installed and a laptop, tablet, or second phone with internet access to run an audio sound source. We recruited Daniel, one of our SMAP students, way down in Texarkana, Texas, to show you how to do the Doppler effect experiment. Let's take a look.
I'm going to be using the Phyphox app to measure the Doppler effect. I'm going to move the phone towards and away from the sound source. Our base frequency was at 800 and it went up around 5 and went down around 5.
In Daniel's experiment, he used a laptop with an audio source set to a frequency of 800 hertz or 800 cycles per second. And just like with the slinky, when Daniel's phone approached the sound source, the waves got shorter, they were compressed. And the phone received those or heard those and recorded those frequencies as a higher frequency, a shorter wavelength, a higher frequency. And as the phone moved away, the wavelengths got longer, which the phone recorded as a lower frequency, a longer wavelength. Now, of course, the frequency produced by the audio source didn't really change. It was a constant frequency. The difference is that the phone received the frequency relative to its motion. A higher frequency moving toward, a lower frequency moving away. A higher frequency because the waves are shorter, coming closer, and a lower frequency because the waves are longer, moving away. We can see from Daniel's graph the changes in frequency recorded by the phone as it moved away from and toward the sound source. We see an increase in frequency. That would mean a shorter wavelength. That would imply that the phone is moving toward the sound source. And then the frequency decreases down to about 795 hertz, implying that the phone was moving away from the sound source. In other words, as the phone moves away, the wavelengths are stretched out, further distance between the wave peaks, and we hear that, the phone hears that, as a lower frequency, a lower pitch.
The Doppler effect is how the observed frequency changes when an object is emitting a sound as it comes closer and away from you. You're standing on the road and a car comes by and it's honking its horn. Right here, the waves are compressed because the car is driving towards you, so the waves will be heard at a higher frequency. But over here, the waves are expanded, so they're at a lower frequency. But when you're in the car, the horn sounds the same the entire time.
For astronomers, these changes in wavelength and frequency are interpreted in terms of light. For a luminous object, an object emitting light moving further away, the light waves are slightly stretched out, or more toward the red or longer wavelength end of the spectrum. Conversely, for an object moving toward the observer, the wavelengths are slightly shorter, shifted more toward the blue end of the spectrum. These shifts in the wavelength and color of light are actually used to calculate how far away galaxies and other objects are and how fast they're moving. Well, that's our first experiment, measuring the Doppler effect. The link for the written handout as well as the teacher guide are provided in the description for this video. And check out our second Doppler effect video, which goes into a little more detail on applications to astronomy and astrophysics. That link is also in the written description. So have fun with Phyphox and doing the Doppler effect experiment. Stay tuned for more fun from Saturday Morning Astrophysics at Purdue.